Lyman-Briggs Physics 2, Building an Electric Motor by Isabella, Taya, and Ethan. We will begin with background information and then look at some representations, our experimental design, data in our graph, a real-world comparison, error we found in our experiment, scientific reasoning, and our conclusion. Before we get into our experiment, here are a couple of terms we'd like to describe. Current is the flow of electrical charge, and magnetic field is the vector field of electric charges with magnetic influence. In this experiment, we investigated how changing the number of magnets in an electric motor changes the force felt by the wire. We found that increasing the amount of magnets had a direct relationship with the force felt by the wire. Additionally, for this experiment, we will assume that magnetic field will always be up, voltage remains constant, current is always constant in magnitude and direction, and the length and shape of our loop will always remain constant. Here is our force diagram with part of our electric motor setup present. You can see that when you change the direction of the force, a change in current direction corresponds.
Our first figure represents the circuit diagram for the system when it is set up correctly. Current flows from the batteries through the loop and back to the battery. Our second figure represents what the magnetic field lines would look like with varying numbers of magnets used in different trials. Increasing the number of magnets increases the concentration of the magnetic field lines. Why does the motor work? The loop spins because the magnetic force on the top is going to push the top loop out of the slide, assuming clockwise current, and the bottom loop into the slide. This process repeats if the current is constantly clockwise. To create a current that always goes clockwise, you have to strip only one side of the loop. If you don't strip one side, the loop can't reset its current to that it is always in one place, and the loop will oscillate in one place. When you strip it, the current can reset clockwise and flip the loop multiple times. So we do have some ideas for improvement. By increasing the magnetic field, we should be able to increase the magnetic force due to properties of the cross product. Increasing the magnitude of the magnetic field increases the magnitude of the force. When the magnetic force increases on the loop, the motor spins faster than before because there is a faster speed on the loop due to an increased acceleration from the force. For our design, we obtained 3 batteries, a wooden block with wires attached, coiled wire, small magnets, and alligator clips. We then attached the alligator clips to the wire perpendicular to the wooden block once ready to take data. We were then able to count the number of revolutions in 20 seconds. We conducted 3 trials, only changing the number of magnets from 1, 3, and 5 for each trial. The data was collected within 20 seconds of a recording in slow motion and then converted to the number of revolutions per minute. The table represents the RPMs calculated for each of the trials with varying numbers of magnets. The orange piece of tape shown in the image helped for us to accurately count the number of rotations in the video. This is a graphical representation of our data. It displays that as you increase the number of magnets, you will see a higher RPM.
In this lab, our model motor generated 351 RPM for a 5-magnet motor. In the real world, brushed DC motors are similar in build and are seen in most toys that require motors. Typically, DC motors have 25,000 to 30,000 RPM without anything loaded in the motor. Our model has significantly less RPM than the toy DC motors. However, it still has the idea of how motor functions on a small scale. Some potential sources of error we could have encountered are stripping the wires incorrectly so that the current wouldn't properly reset, increasing or decreasing our RPM depending on how we stripped it. The video quality was fast at times, so therefore we could have incorrectly counted the number of flips that the loop completed, and the magnets could have not been upright. This messes up our final calculation of force, or in this case RPM, of the motor, because the cross product is also based off of direction in addition to magnitude, which affects the force of the magnets on the motor. In this experiment, we measured RPM of our motor, which is relative to the amount of force the loop experienced during the 20-second time frame, because the loop will flip at an increased rate if there is more force to push the loop. Using the idea of the cross product, using the magnetic field and current to calculate force, increasing the magnetic field would also increase the force based off of the cross product identities and the formula of magnetic force based off of a current and magnetic field, as seen to the right, with magnetic field crossing with current equaling the force as a result. This idea is reinforced with the graphical representation that we had. As we add more magnets, this increases the magnetic field and thus the magnetic force and RPM linearly.